the search and study of exoplanets, I think the first question I want to really answer is what is an exoplanet? And to put it simply, an exoplanet is any planet beyond our solar system. And when you talk about that in general terms, there are really two distinctive categories of exoplanets. The first one I'll talk about are rogue planets. Rogue planets are planets that don't have a star that they orbit. They don't have a host star. And you can break that down even further into two more subcategories. There are what are called planetary mass brown dwarfs, or sometimes called sub brown dwarfs. These objects form in the same way that stars do, but they just never get big enough to go through what's called thermonuclear fusion, which is needed to have something we called a star. And so it's you get these objects that try to get to being a star but never quite make it, and they're about the size, the mass of a planet, which is why they are referred to as planetary mass brown dwarfs. And then the other type are ejected planets. They are literally planets that, they had their host star. They formed the same way that planets in our solar system did, but either something happened with their orbit or something happened to the star. There's some event that occurred that caused the planets to be ejected from the system itself and left the gravity of its host star and is now free roaming through the cosmos. Now, these planets can seem like they'd be really hard to detect because of really not we're not there's no light that's emitted from them. They're not a star. So how do we detect them? It's through this process called gravitational microlensing. It seems complicated. It's not too bad. Uh, all objects have mass, and mass essentially, you know, bends what we consider to be, this sort of plane of sort of space time in a way. Essentially, you can think of if you have a sheet, anything with gravity will pull on that sheet, and so anything that goes near it gets bent in that direction, similar to what we have on screen. And light is no exception. And if something like a rogue planet decides to pass in between us with our telescopes and a star that we're looking at, that light that is heading directly towards us can't reach us because it's hitting the planet, but light emits in all directions. So the light that's just a little off actually gets bent and can get bent and then back and pointed back at us. And so because that happens in both directions, we actually, when an object like a rogue planet passes in front of that star, we see an increase in the brightness. And how much that brightness goes up is actually proportional to the mass of the object that's going in front of it. And so we're able to learn a few things about the object, and in this case the rogue planets. And we're also, once we know that they're there, we can start studying them even further. And so when it comes to rogue planets, the biggest thing that we like to study is sort of the magnetic fields of the moment. It's one of the easier things to look at. And so you can find a few different studies that really looked at some prominent rogue planets and looking at how their magnetic fields compare to, say, planets like Jupiter, who has a wild and huge magnetic field. On the flip side of things, with the on the other side of things, we have planets that still orbit their host star. And so this is a little more common when we talk about exoplanets. We usually end up talking about planets orbiting just other stars. They're a lot easier to detect. There are the main way that we use to detect them is we look at the star and we look at the brightness. We measure the brightness, and if we see when we see a reduction in the brightness, it can mean a couple of different things, but one of the things it can mean is that there's a planet orbiting that star and it just went in front of us, in front of the star relative to us. And again, depending on how much that brightness goes down, is proportional to the mass. And so we can start trying to study these things once we know that they're there. And there are a couple of really fun cases that we can tend to see, such as, hot Jupiters. Hot Jupiters are planets are, around the same size, or if not bigger than Jupiter, and really, really close to their host star. A good example is actually WASP 17b, which is 7.5 times closer to the star, to its host star, than Mercury is to the sun. It orbits its host star in just under 4 days, and its radius is 1.99 that times that of Jupiter. It's almost twice the radius of Jupiter. And what's interesting is in 2013, we actually were able to detect water vapor in its atmosphere. And so just because these things are super close to their host stars doesn't mean the only thing they have is hydrogen and helium. That's usually the case, but that's not always the case. And so it's really fun trying to look at these hot Jupiters, and while they may not be, they may not be, answering the whole question, is there life out there? That doesn't mean they're not, fun to study. Another really interesting cases that we see are multiplanetary systems, systems that have more than one planet around the host star. One of the most infamous ones is the TRAPPIST-1 system, where it has all Earth-sized planets, 7 of them that we've discovered around that one star. And they're all closer to the host star than Venus is to the sun. But at the same time, because the star itself is smaller than our sun, 3 of the planets in that sun are in that system are actually in what's called a star's habitable zone. And so then we get some even more fun, and probably some of the most dangerous to talk about in terms of, how going off on tangents, is potentially habitable planets. Planets in a star's habitable zone. When we talk about a habitable zone, it's essentially it's essentially the distance away from a star where it's possible for liquid water to exist on the surface of the planet if the planet has a surface. And so habitable zones are really fun to talk about when you start going down the conversation of, can life exist on other planets? Because that is the first requirement, is it has to be in the habitable zone. What's a really good example of an interesting exoplanet was actually the exoplanet that I first learned about that got me into looking into this field, which is Kepler 452b. And Kepler 452b is about as far away from its host star as Earth is uh, from the sun. And the host star is about the same mass, but it's I think about 1.5 million years older than our sun, and as a result, it gives off more energy. And so its habitable zone is a little different, but currently Kepler 452b actually still is in the habitable zone. And it's considered essentially what's called a super Earth. It's a little bit bigger, it has more mass than Earth. And it's estimated to have gravity of almost twice as much. But then you get into the conversation that's not talked about a lot with habitable zones, of something that's referred to sometimes as a continuous habitable zone. As a star changes and as a star gets older, the amount of energy that it gives off changes. And the amount of energy, the amount of heat that's released in light that's released from these stars, that's what determines where the habitable zone is, because those are all factors are also determined by its mass. And the mass changes as it gets older as well. And so as the habitable zone shifts, a planet may not always be in the habitable zone. Like with the sun, up until the sun decides to go into its red giant phase and completely consumes the Earth, until that point happens, Earth is actually just barely within the sun's continuous habitable zone. So we got lucky with that in terms of just where the habitable zone tends to sit. And with Kepler 452b, I recently learned that it's not in its host star's continuous habitable zone. So it may only be able to have, it may only be potentially possible to have life on it for another 500 million years or so, which for us seems like forever, but on the timescales of astronomy is the blink of an eye. And so it's interesting to think how, even though whenever you try to talk to someone about can a planet have life on it, this is the thing they talk about. They talk about water on the surface. That's not the only factor. And even with this factor, there's way more to it than we can talk about in, you know, half an hour to an hour. And so that's why I say that this is some of the most sort of dangerous thing to talk about when you really start getting those conversations, because there's so many factors that we try to study and so many factors that we can't study that we just know are there and have to be met, that it really goes into the conversation of, we think this is what it is, but in reality we can't definitively give you an answer, at least not until our technology gets significantly better to study things that we can't study yet. And so until then, we study as much as we can. We've gotten to the point where we can study the atmospheres of planets. One of the ways that we do this is when light's emitted from the host star, and when the planet is passing in front of the star, is when it's what's considered transiting. We can measure that light with a different type of instrument, where we can actually essentially get what's called a spectra, where if you're looking at something that isn't a star, looking at its spectra can actually tell you what elements are in that light, or what elements are that light is passing through, essentially, because different elements absorb different wavelengths of light. And stars, for the most part, emit pretty much all wavelengths of light, with the exception of what they're made of. And when we know what the star is made of, and we measure the light that's coming from the host star while the planet's in front of it, we can also now measure the light that's as it's being absorbed by the planet's atmosphere. And so we can look at the elements within the atmosphere. A similar way of doing this is essentially the same concept, where we look at the light absorbed when the planet is almost anywhere in its orbit, and then we look at the light emitted by the star when the planet is specifically behind the star relative to us. And it's a similar process where we try to determine the elements that are only there when we know that we're looking at light that includes the planet's atmosphere. And so we can actually look at what these planet atmospheres are made of, if there's an atmosphere, which is how we know that in 2013 we found water vapor in the atmosphere of WASP-17b. And so you really start to get into a lot of different ways to do this, and it's very much a growing field, to the point where I'm even doing some research here at Central, where we're trying to determine if our research telescope can detect these planets at all. Uh, we're looking into things like hot Jupiters in multiplanetary systems. HAP-P67b is the largest exoplanets to have ever been confirmed. It's just over 2 times the radius of Jupiter. And we're trying to see if we can detect that with our telescope. And with multiplanetary systems, we're looking at the Kepler 20 system. It has 6 planets. 4 of them are Earth-sized, 2 of them are super Earth-sized. And some of them have orbital periods that are within a couple of weeks. The smallest one being slightly less than 4 days. And so it's possible for us to try and look at the star and see if we can detect those planets going in front of the stars, because it happens often enough where we can try to see, can we do this within the time span of a few quarters here at Central. So even here on the college level, we're looking at trying to do research in this field, and it's we're always learning more, and we're always trying to do more. And while we can only do so much now, I look forward to what we can do in the future. And so that's the majority of what I'm going to be talking. That's really all I have for you, any of you all. Uh, I'm open for questions. I see one in the chat. So, why is a planet's mass important when investigating uh, whatever has crossed the path of light? Um, so if I'm understanding the question correctly, you're talking about the rogue planets and how we detect them with microlensing. The mass isn't the reason that the mass is important is the bigger the mass of the planet, the the higher we're going to see the brightness change. Because essentially, when you're looking at the mass of an object and you're thinking about how it affects the gravity of the space around it, the if you sort of think about it as sort of a fabric being pulled down, the more gravity the larger its gravitational field is, the more it pulls down, and so the deeper that hole is, but also the farther out it tends to have an effect. And because light from a star is emitted in all directions, the bigger that sort of dip is, the wider it is, the more light that can be caught from just off of it, and so it allows more light to be hit the telescope, and thus we read a brighter, the number goes up. And so the mass isn't important in detecting the planet overall. It's just one of the things we can measure from the change in brightness. Um, I see another one. What is the terrain of other planets and the habitable zones like? That's actually something that I've been trying to look into a little bit. It's very hard to figure out simply because the planets are so far away that it's really, really difficult to study specific things like that. We're getting to the point in research where we may be able to start doing things like that soon. There's a lot of promising results and some other things that I've heard about throughout my time at Central. I don't have any specifics just because it's been just on the fly conversations, things that didn't, I wasn't sitting at a computer to look it up all myself. And so it's things that I've heard about, but I know that the technology is almost there. Just we still have a little more to go, because being able to study its atmosphere is one thing, because we know that the light goes through the atmosphere and we're looking at elements. We can't really tell how much per se, or how it's distributed in the plant overall, but we know what elements are there. And it's just like with when you're talking about the surface of planets, we can't at the moment we can't even tell if the planets have a surface or not. I mentioned Kepler 452b being, the thing that got me into this field. We don't even know if Kepler 452b has a surface or not. We don't know if it's a rocky world or if it's a gas world. Uh, we just know how far away it is from its star, and we know that it's really, really close to a lot of some of the factors that we really like about how we know that life can exist on Earth. A lot of those numbers are really similar, so it's likely that it's a rocky world, but we don't know, and there's not a lot of ways to tell. So that's a long way of saying I don't know what the terrain of other planets and habitable zones are like, and most people really don't. There are theories and there are educated guesses, but we have no way of knowing yet.
I have a question, Josh. The image that you have as your background tonight, are those planets sequenced in any specific way, or what's the story behind that graphic?
Are you, if I can actually play with my thing, here we go. Are you referring to the Kepler 62 system?
Oh, is that what that is? Okay.
This graphic here?
So no, I'm referring to the graphic on your Zoom background. Like there's a whole list of
Oh, I forgot
yeah.
that was there.
Oh.
Oh, that's no, that's just a really cool image I found on Google. I
Oh.
don't exactly know really what any of those are. And the thing with a lot of these, I should make sure I make doubly, say that, all of these images that we have, they're artist renditions. We're not able, as cool as it would be to get an image of a hot Jupiter like this, it's not something that we can get. And so these are all artist depictions. And so none of these may even be accurate. It's just information that we know, we take and we try to fill in the gaps to make an idea of what might this look like.
All right, thank you.
Um, so next question down, I see, what other qualities besides water must a planet have in order to be classified as habitable? Long story short, a lot. Some examples are that you actually want to have it's phosphorus. Yeah, phosphorus. You wouldn't be able to detect phosphorus on the planet, and you don't uh, want just phosphorus. You want phosphorus as runoff from land. You want water on the planet, yes, but you want land with water. And the reason for that is because there are materials that, there are compounds that can develop on a dry surface that can't really be developed in the water, that when, if you have rain runoff, whatever the rain is made of, it doesn't particularly matter in most cases. But if you have rain runoff that brings those compounds to the water, uh, that's something that we need to have for life as we know it to essentially be possible. And that actually is part of the reason why life developed in the oceans of Earth, is because we had runoff bringing compounds from the lands to the ocean that then uh, the early life forms or early life organisms were able to utilize. Uh, and you also have things as grand of a scale as where the planet or where the system overall sits in its galaxy. Where we sit in our galaxy is a factor in whether or not we can be habitable, because of how many nearby stars we have. If there's too many stars nearby, the risk of having, supernovas affecting us or gamma ray bursts affecting us, which are, when they're too close, are very, very dangerous to life and overall also just the health of the planet. If there's too many stars, then you run the risk of having that happen too often and life can't evolve. But if you don't have enough stars nearby, then you don't have enough stars dying to provide heavier materials that are needed for life to evolve. Um, so I'm going to keep going with the next one. Does the planet in the habitable zone spin like the Earth does? So all as far as we know, all planets actually do spin, even ones not in the habitable zone. They spin because of when a planet forms. At first, it's just a bunch of dust around the star. And because of the way that gravity works and the way that things are moving in the dust, once the planets start to form, they keep that movement. And so they start to spin. And so uh, not all planets spin the same way, but all planets do spin because of how they form, as far as we know. Um, if we ever find an Earth-like planet, how possible is it that life found on such planets would be more intelligent or advanced than us? That would determine. You could go off of the idea of, how old is the planet or how old is the star. If we tried talking about, well, what about if there was life on Kepler 452b? Our sun is about 5 billion years old. Yes, I think I have. It's either billion or million. My memory is shot right now, but I want to say billion. So I'm gonna go with it until if I'm wrong, someone will correct me. Uh, 5 billion years old, and Kepler 452b is 6.5 billion years old. And so based on that and what we know about the age of, or in the evolution of planets, and what we can estimate the age of Kepler 452 to be, we know that it's at least a few 100 million, if not around a billion, maybe even a billion and a half years further evolved than the Earth is. So if it just so happens that life was possible and did evolve on Kepler 452b, it's had a billion more years to evolve than we have. And at the same time, you have the question of, does that mean they're going to be more advanced, or does it just mean they're older? Because we barely understand ourselves and how we evolve as a society, and what that means for really, really long-term things like astronomical timescales. We can make guesses based on how we act now, but being able to try to determine if planets would have more intelligent or more advanced life forms than us is about as difficult as trying to understand ourselves, which, like I said, is pretty difficult at the moment. Even with all that we've learned, there's still so much we don't know. And I think that really is one of the biggest things that at least drew me to astronomy overall, is there's a lot of things we know, but there's also so much more that we don't know that is within our grasp, or almost within our grasp, to reach. And so it's almost in a way comforting knowing that, with me going into this field, that there are things that we haven't found yet that I get the opportunity to help with, and things that we don't understand now I may help to understand later on. Are there any other questions?
Well, if there's not really any more questions, I want to thank Josh for his presentation, and I want to thank everyone for coming to listen. This will conclude our Star Party.
I will add one further thing. There's going to be one further Star Party this quarter. Somebody in the club can correct me if I'm wrong, in 2 weeks, and then
No, because it's so close to finals week, we aren't gonna do one on the second Tuesday of March, because it's
okay.
literally the week before finals week.
Okay, sounds good. So first Star Party will be in spring quarter then.
Yeah.
Okay. I did a recording. There was a question asking to share the slideshow.
I think Ryan puts them on the website. Ryan, correct me if I'm wrong, but.
Michaela, could you put the website in the chat?
I'll know.